But now if you centered your design, say 100 ohms plus or minus 10%, for instance, and you use the DKXY, the wrong DK. But when you measure it now, it really wants to be DKZ is the real DK. So you've lost 2 or 3 ohms of the positive margin now. So now you really had a, realistically, you've not centered it at 100. It's like 101 realistically. So now you only have 8 ohms of margin left. And now you throw in your process variation, like a little over etch a bit, and, the thicknesses aren't right. You could end up hitting the violation line and they say, oh, scrap, or they call up and say, what do you want us to do with the board?
Hi everyone, it's Judy Warner. Welcome back to this special edition of the Ecosystem Podcast. Today I'm joined by EDI CON presenter Bert Simonovich. Bert will be presenting next week on October 4th about an interesting subject that can help you avoid having pitfalls in regards to your impedance modeling and measurement. I think you're really going to enjoy getting this teaser of Bert's talk, and I will put the link in the show notes so you can sign up and go watch for free next week. Thanks for joining. Now let's jump into our conversation with Bert Simonovich. Hi, Bert. So good to see you, my old friend. It's been a long time, and I'm really excited to talk to you today about EDI CON.
Oh, hi, Judy. It's so nice to see you after so many years. I think it was 4 years ago, or maybe more now, since we saw each other at DesignCon. So always great to see you and catch up.
I know. So last year I was there, but I was podcasting and never got out of my booth. I didn't see anyone. It was horrible. So this year, I promise, we'll find some FaceTime. But in the meantime, why don't you share with our listeners who may not know you a little bit about your background and sort of the areas of interest you have?
Okay, sure, Judy. Well, I'm Bert Simonovich, and I graduated from Mohawk College, and I'm an electronic engineering technologist. I'm a senior member of IEEE, and I serve on the DesignCon program committee and the Signal Integrity Journal editorial advisory board.
Well, I know you concern yourself with a lot of particularly board level SI issues. So first of all, I'm going to ask you a question that's mostly for me, but maybe for our listeners too. We're going to be talking about, here I go, anisotropic. Did I say it right?
No, it's anisotropic properties.
Anisotropic properties.
Yeah.
So will you please define for us anisotropic?
Oh, what anisotropic properties mean is the material property, electrical performance is different depending on the axes. X, Y, or Z axes. And particularly in printed circuit boards, it's related to how the electric fields are orientated toward the PCB laminate. So printed circuit board laminates are made of fiberglass and resin, and they're measured by the fabricators. They have different test methods, over 13 different test methods they could use. And depending on the test method, the electric fields are either in plane with the fibers, the fiberglass, in the dielectric, or out of plane, perpendicular to the fibers. So the implication is transmission lines like to have the electric fields perpendicular, and the DK measured in that way, we call like DKZ for it. Other test methods have the E fields running in plane with the dielectric material. So we denote that as DKXY typically.
Okay.
So DK is the effective permittivity of the material. That's one of the most important parts to get your impedance modeling right. in your 2D field solvers, for instance, or any of the EDA tools. Try to do impedance. Dielectric constant is integral part of that. So, it's an important thing to consider when you're doing your modeling, signal integrity modeling.
So I have a question about that. It's my understanding, don't the laminate manufacturer provide those models? And what is it that you're noticing where there may be some mismatch?
Oh, yes. So typically board shops, they work from construction tables provided by copper-clad laminate suppliers, CCL suppliers.
Mm-hmm.
And for years, they just take the DK and DF values from there. They use that put it into a 2D field solver to predict the impedance when they do their stack-ups.
Mm-hmm.
And then that defines the line width and space, all the things that's involved in the stack-up.
Right.
So because DK is important, if you use the wrong value that's been measured, your impedance will be wrong. Fortunately, most laminate suppliers measure the laminate in DKZ, or out of plane. And for the most part, the impedance will come out right, should come out right. The line width is right, everything should come out right. But now there are some laminate suppliers, Asian ones, they use what they call split post dielectric resonator. And it's a simple test. And by the way, these IPC tests are really designed for quality control. They're not designed to provide accurate numbers really for signal integrity or anything like that.
Got it.
And they state that in their construction tables. But generally, they're good enough to do your impedance for it. So when they do the stack-up design, the DKZ is there. So some laminate suppliers, they say they use XY. If you use those numbers when you do your characteristic impedance modeling, after you build the board, if it was made exactly as the stack-up, like no process control, your impedance will end up being higher.
Right.
When you measure it.
So this is what you're going to be talking about specifically is you've been researching this dynamic, specifically looking at all those variables.
Right. And the reason I started doing it is helping clients. I've experienced that. Like, why are my impedances wrong? Because we're using a different laminate that's measured in XY. And when you start drilling down into it, then you realize, oh, there's anisotropic effect in there.
I see. So you've been researching this, Bert, from what you told me before our podcast. You've been researching this because you saw it. You have a consultancy, and you saw this happening with clients. And so you started following, you went down this rabbit hole and started finding these unusual effects and why. And so you're going to do a 25-minute talk. What else did you discover along the way of digging into your clients' problems with anisotropic effects and the different ways that, in plane, out of plane, whether it's X, Y, or Z access. So you're saying that if you just go with IPC specs in your board manufacturer, but you have a desired outcome for signal integrity purposes, they're not going to line up.
IPC spec for the TDR measurement is 20 years. Let's just say it's 20 years, the last revision. 20 years ago, our line widths were wider, typically 5-6 mils type of thing. Mm-hmm. We're using 1 ounce copper, and our dielectric material was pretty lossy. FR4 was pretty much it. It was pretty lossy. When the board shop when they design the stack up, they use a 2D field solver to do the impedance. A 2D field solver is a lossless calculation. It's not lossy. So, but when you do a TDR measurement, it's a lossy measurement defined by the IPC. And basically, if you ever looked at a TDR measurement on a screen, you see it starts off on the left-hand side and then has a slow, gradual rise. And that's caused mainly by the DC loss of the trace, upper loss. Couple that with the very low loss material we're using today, that slope is fairly steep. So today we use very narrow line widths, like 3 mils, pretty narrow, 1/2 ounce copper. And as I say, the dielectric material is very, is low loss, very low loss.
Right.
Well, the low loss also helps to flatten that, or the higher loss helps to flatten that curve. So 20 years ago, even though there was copper loss and everything, the higher loss material tended to flatten it. So even though it was a lossy measurement, where they measured between 30 and 70%, that's why you had your tolerance of 10%. Everything was pretty close, and you could build boards and not have an issue. But today, as I say, with the low loss material and the thin line widths, that has that rise. So without anisotropy, you could have a problem in the process variation. The real impedance you want to measure is down near the beginning of the TDR plot at the start. That's really will match with what you've predicted. If you're measuring up there and it's violating, it's not truly the measurement. But, we've been used to that and things generally work okay. But now if you centered your design, say 100 ohms plus and minus 10%, for instance, and you use the DKXY, the wrong DK. But when you measure it now, it really wants to be DKZ is the real DK. So you've lost 2 or 3 ohms of the positive margin now. So now you really at realistically, you've not centered it at 100. It's like 101 realistically. So now you only have 8 ohms of margin left. And now you throw in your process variation, like a little over etch a bit, and, the thickness is not right. You could end up hitting the violation line and they say, oh, scrap, or they call up and say, what do you want us to do with the board? So generally then we look at it and say, oh no, it's down here, so it's okay. But if you use the right DK, then you would center it properly and things would be right. So that's the one problem for SI, is the impedance for the traces. But there's another issue now with vias. Vias go the opposite. They go in the Z direction in.
Correct.
So the DK it wants to see when you model is really DKXY, or in plane. So if you only use one number for DK, one or the other will be wrong. So if you use DKZ for the transmission line, that'll be right, but the VIA will be inaccurate, the model. And vice versa.
That's really interesting. So, Bert, I'm wondering why you notice it now. Like I'm assuming it's speed or frequency or something that's driving it. Like you said, that when the spec for IPC was made 20 years ago, it sounded more forgiving. So what's driving this, and what made you come across this?
Okay, good point. 20 years ago also was bit rates for 1 gig serial lengths. Today they're 100 gig.
Yeah.
Right? An order of magnitude difference. And at 100 gig, 56 gig even, but 100 gig, everything matters even more.
Yeah.
And, that's the problem. So in the past, you probably had enough margins and things, but today those margins are eaten up. And it involves accurate modeling. You need a sharp pencil today.
Right. That totally makes sense. Everybody's saying it. Everybody's saying right now, Bert, that the way people are framing it to me on the podcast anyways, is that as these speeds increase or the frequencies increase, we think we're just going to sort of scale or something, but the actual rules of thumb don't apply anymore. Like we need new.
Yeah. Not today. You need
Yeah.
accurate modeling.
Accurate modeling, right? Which is, I can't tell you, in the last month, probably the last 3 podcasts I've done, they've talked about this modeling, the problem with models. And now, I mean, we were talking about the models of chips and different package speeds, this and that and the other thing. But this has to do, it's a board effect, right? Because you have this laminate that's constructed in a way, and the electrical fields are moving through the laminate. So I could see how it would be overlooked. Okay, so you're gonna go ahead.
More importantly, as well, is with the EDA tools that we have today.
I see.
Not a problem with it. EDA tools are accurate as what you put into it. They're very good.
Yes.
They're solvers, everything into it. But now, if you think about it, many EDA tools are moving toward this AI stuff, like making it easier, push button things, get results. Feed it your layout, it'll extract it. If your stack up's got numbers in it, it'll give you answers. Well, now,
But are the answers right?
right. So now, if your tool doesn't allow for anisotropic effect, what decay does, which part of that channel to use? It'll just pick the decay from the stack up that it imports.
Right.
But that's one decay. You need
Right.
2, basically, or to know the anisotropic effect of the material so you could put into a tool. And not all the tools have that capability.
I
So
see.
this is just one thing to be aware of as well. When you're doing that extraction, to think about that and see if your tool has that capability in it.
Well, this
to be
is
able to do.
fascinating. I think this is going to be really valuable. Now, I know you're doing, do you have a date that you're presenting at EDI CON?
Yes, it's October 4th.
Okay.
I think it's in the afternoon after lunch.
Okay.
So not sure the time. They have it on the
Okay.
website. The schedule's there. And that's the first session of October. And I'm doing it then.
Well, I know because I've talked to Pat Hendel at SIJ and I've talked to Ben Dannon also. They're giving you a whopping 25 minutes, right? Because the online, attention spans, like we're all burned out
Right.
with webinars and stuff. So you can only get so much in. So as I understand it, you're going to give a 25-minute talk on the subject, hopefully gives engineers some ways to manage this more effectively and be aware of it. And then, but you're going to be doing, like, I think of this as a primer for a much larger presentation you'll be doing at DesignCon.
That's right.
So can you tell us a little bit about how far you are? I mean, maybe you're not done with that presentation yet, but, the length of time you're going to have and, just tease up a bit of DesignCon as well. And we can have another conversation before then.
Yeah. So for EDI CON, really, it's like you say, it's a primer. But in order to understand see, I can't say it.
See, now I screwed you up, Bert.
To understand anisotropic effect, you have to really understand how boards are fabricated, but not just from the PCB shop. I'm going to start off from really from raw materials, showing you get the glass fibers, how you mix it, and really have, take you through that little bit of a journey as a bit of a background to get you on a baseline. Then when I start talking about the anisotropic properties and what that is, the physics about it, you'll have a better understanding with it.
Right.
And then I'll show some examples, just quick examples of, especially